Hello everyone. Today I'm going to take the live session number 12 of the NPTEL SAM designed course named Chemical Crystallography, which has been taught by Professor Anshuman Rajoguri from ISM Mohali. So, sir has been teaching us from the starting date was 24th of July, and this course has the ending today only, that is 13th of October. Now, I'm going to take one summary session on this Sunday at 5 p.m. And the exam date for whoever has registered for the exam is 20th of October. I hope whoever is willing to has already registered for the exam. Now, I'm the TA of this course. I'm Shani Burman from the Department of Chemistry, IIT Hyderabad. Now, uh, let's start today's session. So in week 12, Sarah taught how to index the PXRD peaks using the Debye-Shannon method and how to like process the raw data from what we have got from the single crystal X-ray diffraction machine to detect one single crystal or a cracked crystal. And then Sarah taught what are polymorphs and how they are characterized, how they are distinguished, etc. Now, this problem solving session is contained from the questions of week 11 and 12. So from week 11 and 12 learnings, I have picked up some questions. So the first one is a comparison of simulated PXRD pattern of a crystal with the experimental pattern of the bulk can identify the presence of polymorphism. What do you think? What will be the answer? So the answer is true. Okay, let me just select first. So the comparison of simulated pattern, let's say if this is, wait, just a sec. Let's say if this is, if, just a sec. Huh. So if this is your PXRD pattern, let's say, then this will be the same simulated pattern, right? This is experimental, this is simulated. Simulated means obtained from the zip files. Zip files, from where we will get the zip files? Zip files will be getting from the single crystal XRD. And when we solve the crystal structure using maybe the ONIX software, then we get the from the result file we generate the zip file, the crystal identification file. So, if this is the simulated pattern, experimental pattern, then we can distinguish using both of them the presence of polymorphism, right? So, what is polymorphism? That will come into that will encounter in later questions. So then only I'll answer. Now the next question is the powder diffraction data consists of a record of photon intensity versus detector angle theta. So this is only the powder diffraction data, this one only. So, in this uh, y axis, it is intensity. Okay, intensity is such that, let's say, this much is 100 and this much is 0. So you can say this is 10, then 20, 30, 40, 50, 60, 70, whatever it is. So like that it will go. Like that, numbering the labels we put in the y-axis, and in the x-axis it is, yeah, it is detector angle, but it is in degree in 2 theta, or 2 theta we write, and in bracket the unit is degree, and here the unit is arbitrary unit. Okay, so this is 2 theta. Okay, not theta. So it's intensity versus 2 theta, y versus x axis. Okay, so this is false. The next one is k alpha 1 and k alpha 2. K alpha 1 and K alpha 2 doublet will almost always be present. Now, these are called the dual wavelength or the double beam XRD setups. So, why both of these lines are employed? Because there are some reasons. Maybe the first one I'll tell is um wavelength discrepancy. So, in X-ray tubes used in the XRD instrument often produce characteristic X-ray radiation with two closely spaced lines. You already know these lines are K alpha 1 and K alpha 2. The K alpha 1 line is slightly shorter wavelength, has slightly shorter wavelength than K alpha 2. I'll first write the reason is wavelength discrepancy, or the doublet lines. So it's like this. Say this is K alpha 1, this is K alpha 2. If this is wavelength, let's say, then this is alpha 1, this is alpha 2. Okay. The next one is resolution enhancement. So using both the K alpha 1 and K alpha 2 lines allows improved resolution. Okay. And next one is correction of absorption effects. Sorry. Absorption effect correction. So what does it do? Samples will absorb X-rays like differently depending upon their wavelength. Now by utilizing both of the K alpha 1 and K alpha 2 lines, we can correct the absorption effect, especially for samples with variations in composition or thickness. The next one, the reason is elimination of systematic errors. So by using both of the lines, they will help you in identifying and correcting the systematic errors. So these errors can include instrumental artifacts, crystal misalignment, or other factors that might affect the accuracy of the diffraction pattern. Okay. Now the next one is quantitative analysis. So these lines will help in refining and improving the accuracy of the analysis by considering the intensity ratios of these doublet lines. Okay, so it will enhance both, like always, the overall performance of the PXRD instruments and the diffraction data we get. Okay, so it should always be present. The next one is EADP command adds the equivalent ADPs command for all atoms sharing one site. Yes, it's true. EADP is that only, right? Yeah. So EADP is same. This is the equivalent ADP. ADP means atomic displacement parameter. So it's used to find the find the atoms of sharing only one side. Now ADPs describe the spread or thermal vibrations of atoms in a crystal structure. So when atoms share a site, it means they occupy the same position in the crystal lattice. And EADP, the equivalent ADP command, adds the same ADP command for all atoms sharing one site. Okay. Now the next one is in a theta to theta instrument following Brentano geometry. Always remember this is for sample and this is for detector. Okay. And where the source is fixed. The sample theta, detector 2 theta. Any other? No, there is no. So and the source is fixed. So this is the option. If temperature increases, the PXRD. uh, If temperature increases, the peaks in PXRD shifts to it is shifts to lower angle. Okay. So now what happens in powder XRD? The position of diffraction peaks, uh, yeah, is influenced by various factors like temperature is one of them. So this is due to thermal expansion of the crystal lattice. When you provide heat or temperature to your sample, the lattice structure may expand due to the increasing thermal motion of the atoms due to the temperature in the molecule in the crystal. So this expansion leads to a decrease in interatomic distance, which in interatomic distance means, okay. So D is inversely proportional to sine theta, right? And in PSRD pattern, the x-axis is 2 theta, which in sense like theta only. So this will shift to lower angle means theta will be lower. Right. To be theta become lower, D has to be higher. Right. So temperature, providing temperature means expansion of the lattice and interatomic distances increases and theta will be lower means shift the peaks. If this is the first peak, then the second peak will come around this. This is for temperature. Okay. And this one is for, let's say, room temperature. Next one is the dynamic disorder in crystal structures is due to thermal motion. Okay. Thermal motion arising from the temperature effects. And do you remember for which? static disorder happens. So static disorders are because the location or the position of the atoms, right? But dynamic disorder due to thermal motion. The next one is, what are the indications of disorder in a crystal structure? So both of them due to the thermal motion, elongated thermal ellipsoids, this one, and also the location, multiple locations, or yeah, like misplacing of the atoms. So appearance of Q peaks at location that form a chemically sensitive alternative conformation. Yeah, that's true. That's also true. So this will be the answer. All of the above. Now the next one is okay. Commands are given, and here on the left side, in 1, 2, 3, 4, and in ABCD, they have given the function of the commands. So we have just now talked about EADP, the equivalent atomic displacement parameter. And see, here it is also given this one. So 2 will be C. So this will be scrapped out, this will be scratched out. Now, EADP and EXYZ, the next option, the number 3, is almost functions the same. So it is also constraining atoms to the same side. So 3 will be D. See, then easy will be the first option. So affix will be D in the sense refinement constraints, and if VAR is to link parameters through a free variable. Okay. So the next one is, which of the following groups show disorder commonly? CF3 group. What is the structure of CF3? CF. Let's go this. Then perchlorate, ClO4. ClO4. Ethyl group. Ethyl group is CH3, CH2, right? So, from the structures, what are the common things you can look at? So, all of these structures are almost showing tetrahedral geometry. Now, tetrahedral compounds exhibit disorder due to the nature of the coordination and the flexibility of certain molecules or ions within the structure. So, why it is? Because one of the reason is symmetry and flexibility. Tetrahedral coordination allows for a certain degree of symmetry, and some molecules or ions can easily rotate within this geometry. This flexibility can lead to disorder as the positions of the components become interchangeable, right? Now, the next one is ligand exchange. In tetrahedral complexes, ligands can often exchange, and this can result in disorder, like due to if the eligibility for ligand exchange is low, then the next is dynamic processes. Means the tetrahedral arrangement may allow for dynamic processes such as ligand rotation or vibration, which can contribute to the disorder in the arrangement of ligands around the central atom. The next one is temperature effect. Temperature also can influence the disorder in the tetrahedral compounds. As temperature increases, thermal motion becomes very high. Right. So this contributes to the dynamic disorder. And the fifth one is steric hindrance, steric effect. Now, steric hindrance or the repulsion between the electron clouds can affect the stability of specific orientations within the tetrahedral arrangement. Okay. So this can lead to disorder as molecules or ions seek energetically favorable positions. So all of the above will be the option. The next one is which of the following is not related to powder X-ray diffraction. The answer is rotation photograph. Okay. So it's not related to powder X-ray. Now, how Debye-Scherrer method? The Debye-Scherrer method is for powdered samples, right? While Brentano method geometry and parallel beam geometry offer efficient setups for analyzing powder samples and crystal structures in various methods. So the advantage, let's say, the Debye-Scherrer method is used for particularly studying powders and obtaining information about the crystal structure, phases, and crystallite size. Just right there. Bragg-Brentano geometry is used for phase identification, crystallinity determination, and structural analysis of the powdered sample. Now, parallel beam geometry, it is for indexing, texture analysis, and high resolution powder diffraction. Now, next question is the why is the sample rotated in the pixar? It's because to remove special orientation effect. Okay. We also call it like preferential orientation. To remove that, we do rotate the sample of PXRD and get the X-rays from the from where the from most of the angles the X-rays can come. Next one is Which statement from the following is not true about polymorphs? They may have different universal parameters. Yeah, they do have. Then they may have different space groups. That's true. If they have different space groups, they may have different crystals. And yeah, that's what the definition of for the polymorphs, right? The next one, they should have different chemical composition. No. So this will be the answer. It's not. The next one is what is true about a triple point. Triple point is one component system with three phases. This one. It doesn't contain three degrees of freedom or three component system with one phase, or it has only one degree of freedom. No. So we'll just draw a structure, a phase diagram. So like this. So this is pressure, this is temperature. This is for water. This, this. This solid, liquid, and vapor. And this point is called triple point. Three phases with one component is called triple point. Now the next one is polymorphs cannot be identified via which of the following methods. PXRD we are just studying. Yes, we can write PXRD. Raman also we can use due to the the bond stretching and all. This is equals to XRD also. If with any XRD we can detect. And for UV-based spectroscopy we can't because maybe the transitions will be the same, so we can't. So that's. And the next one is PXRD experiment cannot be done for an amorphous compound. No, it's wrong. We can do for amorphous compound. The next one is both K alpha 1 and K alpha 2 are used in PXRD. Yes, we just discussed we will use both of them. Next one is PXRD helps in identification of phases. Yes, that's what we use PXRD for. Single crystal XRD we use to detect about the unit cell parameters, bond angles, bond lengths, etc. But PXRD is for fluid identification. Next one is an amorphous form may represent a polymorph. No, a polymorph cannot be represented by an amorphous form because a polymorph needs to be crystalline and it has to be stable or to exist in different crystal systems. But so it has to be crystalline. Now the next one is amorphous samples do not diffract X-rays. This is the same question as the this one. In PXRT, we can done amorphous compound or the amorphous samples can diffract X-rays. This is the same question. But here it is written amorphous samples do not diffract X-rays, true or false. So it will be false because they can. Now the next is in the Debye-Scherrer method, the powder sample follows Bragg's law to produce cones of diffracted beams. Now, Debye-Scherrer method is used to determine the crystal structure of a powder crystalline material. So, in a powdered sample, when you put the powder sample in the X-ray diffractometer instrument, it will give random orientation of the crystallites, right? So due to this, X-rays are diffracted by various crystal planes at different angles. Now Bragg's law is satisfied for all these diffracted crystal planes in the sample, producing a set of diffraction cones. Now, each crystallite will produce a set of different spots, diffraction spots, right? That means the combination of all the spots results in a diffraction pattern lately. So it's true. Now, the next one is polymorphs can have different universal parameters but cannot belong to different crystal systems. No, it's wrong. It should belong to different crystal systems. So it's false. Next one is the cissoid and transoid forms of an organic molecules are polymorphs of each other. Means, let's say XXHH and XHXH. This is cis, this is trans. These are not the polymorphs, these are rather geometrical isomers we call it. So this is false. In a monotropic system, the stable form at room temperature can be obtained by heating the metastable form at any temperature. Let me give an example of the diamond and graphite. So diamond is metastable. If it wants to convert to graphite, which is stable, right? And which is stable, so it needs heat because this is kinetically controlled. If you do not provide heat, then it will take several years. Like generally, that's what it takes. So heat can provide. If heat can be provided, then the metastable form can can be stable at room temperature by obtaining the stable form. Okay, so it's true. Now the next one is polymorphism occurring due to packing in a different 3D arrangement is called as packing polymorphs actually. But I'll tell you the conformation polymorphs are where the molecules changes conformation and crystallizes as a different structure. Right. These are all insert slides, okay? And then the packing polymorphs, where the compound crystallizes in different 3D arrangement. That's what it's written in the question. But maintains the conformation of the molecule. Here conformation changes, here conformation doesn't change, right? Now, the next one is the pseudopolymorphs. We also calls it solvomorphs or solvents. So it involves solvents in the crystal structures. Could be about solvents. The next one is the concomitant polymorphs. When two or more crystalline forms grow in same crystallization setup under same condition. Those are called concomitant polymorphs. So the answer of this question will be packing polymorph. The next one is the below plot is an example of tautomeric, monotropic, enantiotropic, and pseudopolymorphism. So, firstly, we need to know like what are these terms are being called, right? So, first one is the tautomeric. So, tautomeric polymorphism is you already know what are tautomers, right? In organic chemistry, so tautomerism is a type of structural isomerism in organic chemistry where isomeric compounds rapidly interconvert through the migration of hydrogen atom and a bond. Let's say the different forms called tautomers and polymorphism is already I have told you. So the combination of tautomerism and polymorphism can lead to different crystalline forms of a compound. each associated with a specific tautomeric structure. Okay. So this tautomeric polymorphism uh, is important because they have different physical properties, including solubility, stability, and bioavailability. The next one is monotropic polymorphism. So, monotropic polymorphism is a situation when one crystalline form of a substance is thermodynamically more stable than all other forms over the entire range of temperatures and pressures. In other words, the more stable polymorph is favored regardless of the conditions, and the transformation from the stable polymorph to the others are not possible. Okay. The next one is enantiotropic polymorphism. Now, in enantiotropic polymorphism is when two or more crystalline forms of a substance are thermodynamically stable under different conditions such as temperature, pressure, etc. So these different forms can coexist at equilibrium but are stable at different regions in the phase diagram. And from the phase diagram, that one is the one given in the question. It seems the same, right? Two polymorphs can exist in like different temperature conditions, and they coexist in equilibrium and also stable at different regions in the phase diagram. So this is the option in anisotropic polymorphism. But we should also know what is pseudopolymorphism. So pseudopolymorphism is a situation when a substance appears to exhibit polymorphism, but upon closing the examination, the observed differences are due to factors other than a change in the crystal structure. Okay, let's say a substance might be observed in different forms under certain conditions, but these variations could be attributed to factors such as solvation, hydration, or presence of impurities rather than change in the crystal structure. Okay, so that's what pseudopolymorphism is about. The next one is the Debye-Scherrer method is used to do what? What is the question has been asked on the function of the Debye-Scherrer method. So you already know that it is used to index H-scale planes from the PXRD pattern. Now the next one is for values of 2 theta equals to 8.01 and 9.87 in any specific crystal system. What is the probable H scale among the following? First, we'll write the Bragg's law. Okay, this is very important. N lambda equals to 2d HKL sine theta, or DHKL equals to, it's a n lambda by 2. That means let's say a constant into 1 by sine theta. So we'll first write the 2 theta value, 8.01 and 9.87. Now, theta value would be what? 4 point, like just to have to divide by 3. 4.005, and the next one is 4.985. Right. So the sine square theta value would be like sine theta square value. So it is, if we calculate, it is 0.00488 and 0.00741. Now the next one we should do is sine theta by sine theta 1 whole square. Okay. So this is the theta 1 and this is, let's say, theta n. Here n is 2, theta 2. So sine square theta 2 by sine square theta 1. With sine square theta n can be anything. So for the first one, n is 1, right? So sine square theta 1 divided by sine square theta 1. So it will be the same, just 1. Means 0.00488 divided by 0.00488. It equals to 1. The next one is the same sine square theta 2 divided by sine square theta 1. So it will 0.00741 divided by 0.00488 and it comes around 1.52. Now we'll do h square plus k square plus l square. So the sum of the values can not be 1, right? Because all has some certain value. So we have added 2, like multiplied by 2, and if we multiply this by also 2, this will be 3.04. Now the next one is 3.04. Like we'll take integer values. So it will be 2 will be 2 and 3.04 will be 3. Now HKL will find out 2 will be what will be the value of HKL so that the h square plus k square plus l square equals to 0. So it is 110. You can write it as 101 or 011, etc. And the next one is, is there any option 110? Yeah, the first option. So first will be the option. Next one is 3. 3 is very easy. 1 square plus 1 square plus 1 square. Now the next one is the highlighted, not written there. Yeah. The highlighted spots in the frame represents, this is for the cracked crystal, right? So you should remember this. This is for the cracked crystals. Next one is which among the following is true for monoclinic crystal system. So monoclinic crystal system, the reciprocal lattice is B star equals to 1 by B. The next one is match the following wavelengths with their respective elements worth. So you already know that molybdenum is 0.71 only and copper is 1.54 only. This is what we usually talked about and most commonly used. So let's find for 1 is 1 is 1, D or D में कोई होगा. Then the next one is 2 is 2, 2 is 2, same. So the next one will be the deciding factor, 3 is 3 or 3 is 5. 1.94, 1.79. So it is 1.94 for iron. For chromium, it is 2.29 and for cobalt it is 1.79. The next one is large sphere gives access to larger reciprocal lattice. Large sphere means large Ewald sphere means shorter lambda radiation, right? So it will provide high resolution in the reciprocal lattice, means it will be beneficial to resolve smaller features in the crystal structure. Yes, it's true. The next one is limiting sphere is also known as the sphere of reflection. No, those are two different things. Oh, do you remember the drawing? So this is the X4, this is the center. If this much is 1 by lambda, then this much will be 2 by lambda, right? And this is one is called limiting sphere, and this is sphere of reciprocal. So geometrically, all the reciprocal points that falls within this sphere, the limiting sphere, uh, by rotation of the crystal which is placed where, can be made to pass through the sphere. Okay. So limiting sphere is not known as a sphere of reflection, whether they do have different functions. Now the next one is diamond and graphenes are dash of each other. So they are basically allotropes of each other. But we need to know what each terms are called. So there are options given: polymorphs, allotropes, isotopes, and isomers. So I'll just give you like two or three line about each of them. So polymorphs, you already know, it's basically different crystalline forms of the same material, same chemical composition, but different arrangement of the atoms or molecules. Like carbon dioxide used in different pharmaceutical industries. Now the next one is allotropes. Allotropes are different structural forms of the same element occurring in the same physical state and have the same number of protons but different arrangement of atoms. Okay. So the first one is different crystalline forms of same substance, and allotropes is different structural form of the same substance. The next one is isotopes. Isotopes are variants of chemical element with the same number of protons but different numbers of neutrons, right? Isotopes we often use like hydrogen, deuterium, etc., tritium, etc. So isotopes share the same chemical properties but can have different physical properties due to the varying uh, atomic masses. The next one is isomers. So molecules with the same molecular formula but different arrangement of atoms leading to the distinct chemical or physical properties, like structural isomers like butane, isobutane, etc. Okay, so these are about this. Okay, thank you for listening. Week 12 assignment has already been uploaded in the portal. The submission deadline is 18th of October. I hope you have done the assignment and you surely submit. Okay, thank you.